Yeah, I think you're good to go.
Hi, everyone. Today I'll present on the Hamiltonian Monte Carlo Markov chain. And these are the two references that I've used for this presentation. The first one is very intuitive and conceptual introduction, and it's also very readable, and that's the one that I've used mostly. And the second one is more technical. It has more proofs and also some extensions to the algorithm. So the general problem statement for the algorithm can be that we want to obtain a sequence of random samples that converge to a target distribution from which direct sampling may be difficult. So I think it's also the basic problem statement for the Monte Carlo Markov chain algorithms. And I was hoping to motivate with I think this was the first Monte Carlo Markov chain algorithm called the random walk metropolis. So in this algorithm, what we do is we propose a step in the parameter space of the target distribution with the probability density, also called the transition function. And then we either accept or reject the step with the following metropolis criterion. And in most instances, the covariance of the proposal probability density for the multidimensional cases can be tuned so that they are confined to the regions of high probability mass. So the problem with this algorithm is that it is quite inefficient. It works well in low dimensions with well-defined target distributions, but it has pretty slow exploration, leading to some autocorrelations and biased estimations. So the main idea that people have used, in addition to this random walk metropolis, is to use the geometric structure of the target distribution to direct the transitions themselves. And that's the main idea behind the MCMC using Hamiltonian dynamics. So I think in low dimensional cases, if we take like a one-dimensional Gaussian, we can kind of reason that the high probability regions would be concentrated around the mode. But in higher dimensional cases, I found this to be quite a little bit counterintuitive, but instead of the high regions of high probability mass and the concentrated being around the mode in the parameter space, it actually has geometric structures that are not simple to define. So for example, this is the figure from the first reference, and this is showing when the pi of Q is the target distribution, and then when it is far away from the mode for the 10-dimensional Gaussian, and also another thing is that since when we have a target distribution, some of the quantities that we're interested in are like the expectation values and in other moments. So to do that, we have to do an integral. So in that case, the integral volume is actually concentrated away from the mode in most high dimensional cases.
So can you give an introduction about what Q is and what DQ is, and is it a vector or a scalar in this high dimension?
Yeah, Q is the parameter of the target distribution. So in this figure, I think it's a vector of length 10. And then DQ is when we think about the volume integration, is the incremental step in the parameter space. And pi Q DQ is the integrand. So I think what this figure shows is that instead of the high so the inefficiency of the random walk metropolis comes because it uses a lot of computational resources in areas that have low probability mass in the parameter space, especially in the high dimensional cases. So we like to first figure out what they call the typical set, which is these regions of high probability in the parameter space. And it is dependent on the target distribution itself.
So DQ is the spacing between parameters
Yeah.
to integrate them?
Yeah.
And so just to be clear, the 5Q is in the choose?
Yeah, that's the one that we want to sample from, the target
You want to
distribution.
estimate.
Yeah.
Why is the DQ plot going to infinity?
Yeah. I don't know the exact details of how they came up with this plot, but I think it was more of explanation that the DQ is because in the higher like 2-dimensional or 3-dimensional spaces, the volume around the mode is relatively small compared to the volume outside the mode. And then as you go away from the mode, then the volume increases. But I don't know why it is increasing.
Yeah, probably because like most of the Q are around the mode, right? So the spacing will be more away from it, I guess. Right?
Yeah, I think I think what I wanted to convey with this plot, I guess, is just that we need to keep the geometric structures of the distribution in mind when we're doing the sampling. And then, so what they call the typical sets is, so we want to concentrate our computational resources on those regions of high probability. So the typical sets, and in higher dimensional cases, there are these contours in the typical sets that we can integrate around to obtain the samples. So for example, we have to, so in that case, along these contours, we have to have conservative dynamics so that they are conserved so that the parameters, so we know that there are these regions called typical sets in the distribution space, and then within these regions there are these contours that we would like to ideally sample around, so that we are only sampling in these high probability regions. So, and one information that is readily available to us is the gradients of the target distribution, but only using the gradient would indicate that we are always be conversion to the mode region, which is not ideal because from the previous plot, we saw that we would ideally like to sample from these typical sets, which may not be centered around the node. So it's analogous to the problem in the classical mechanics, the Hamiltonian dynamics, where they have so in order to sort of mimic this process, we also need to introduce auxiliary momentum variable in addition to the gradients. And then as part of the properties of the Hamiltonian, we would also have conserved dynamics along these contours, which they call trajectories. So these are, I think the Hamiltonian dynamics essentially describes the total energy in the system, which is conserved and is a function of Q, which is the position, and P is the momentum. And the bottom two are what are called the Hamiltonian equations. And we can integrate either numerically or exactly to obtain how the position and the momentum variables would change with respect to the Hamiltonian. But along these trajectories, the Hamiltonian is conserved. So we like to ideally connect our probabilistic model to the physical model that are described by the Hamiltonian dynamics. And with that, we can then obtain the conserved trajectories along the contours in the typical sets. Yeah, the most important property of the Hamiltonian that people use in the Hamiltonian MCMC is the conservation of the Hamiltonian. So in the phase space shown here in P and Q space, we see that these are energy level sets that are present. As along these trajectories, the Hamiltonians are conserved. And another important thing, implication of that is that the volume is preserved in phase space, so that if we change the position variable, for example, then the momentum variable has to compensate in the opposite way to keep the volume the same. So MCMC using Hamiltonian dynamics is, we first introduce an auxiliary momentum variable so that it becomes the Q, which is the parameter of the target distribution, and then P that we introduce becomes a 2D phase space. So that the phase space volumes are invariant. So so this auxiliary momentum variable that we are trying to introduce so the important property that we have to keep in mind is that we have to first define a joint probability distribution of pi of P and Q on phase space, so that when the auxiliary momentum is marginalized, we can recover our target distribution. And an implication of that is that, so when we look at the typical sets in the joint probability distribution space, then these project to the typical sets in the target distribution space. So that once we define these, then we can use the Hamiltonian equations and then project back onto the target distribution space. So the joint probability distribution in the phase space can be defined as follows, where we have the conditional probability and the target distribution pi of Q that we have originally. And then it is defined as the negative exponent of the Hamiltonian. So then when we look at the Hamiltonian itself, then we can break it down further into the kinetic and potential energies, where the potential energy is essentially just the negative log of the target distribution that we're interested in. And the kinetic energy is the negative log of the conditional distribution. And then that's something that is, in practice, people do a lot of tuning to find what the exact form of that kinetic energy should be. So for the choice of the kinetic energies, the important thing is that the energy level sets in the phase space of the Hamiltonians are as uniform as possible, so that there are no high curvatures and no features that can bias the estimations. And in practice, the people use the Gaussian kinetic energies with either predefined covariance, or people also, what they do is they have they first run it without any preconditions, and then for a few iterations, and then they use the empirical estimates of the covariances of the target distribution as the M in the equation. And that has been shown to be empirically pretty efficient. So and then now that we have the general structures of the Hamiltonian and the conditional probabilities and other things. So the basic step of the algorithm is that we first sample, the first one should be there, but we first sample the momentum variable from the conditional probability that we define. And then once we have this, then we can integrate it along using the Hamiltonian equations that were defined before. And then at the end of the integration, take the position variable in this case, which would be the parameter in the parameter space of the target distribution, and then use that as, and ideally that would be within the typical set defined by the target distribution. So we can take that as one sample that we have sampled from the target distribution. And for the integration steps, the people normally use what's called the symplectic integrators. And these also preserve the phase space volume so that it limits the numerical errors, and then the numerical solutions normally oscillating around the exact solutions. So one popular choice for this numerical integrator is the leapfrog, but there's still also bias due to errors that can come about. And sometimes I think with this algorithm, it's pretty like problem specific. So people have to tune a lot of, there are like three main things that people have to tune for particular target distributions. And one of them is the choice of the integrator. So, and the bottom is the pseudocode for the leapfrog integrator, where, so we have the inputs are the integration time and the step size and the initial conditions and the gradient of the target distribution. And then we integrate it for the predefined amount of steps following we first, so I think the leapfrog is that people first update the momentum variable at half a step, and then update the position variable a full step, and then do the remaining half step of the momentum variable. So as I mentioned before, there are still numerical errors with these integration schemes. And then the workaround is to use the Hamiltonian transition as the proposal for the metropolis distance accept/reject. And one thing that we have to keep in mind when we do this is to make the transition reversible. So in order to do that, we have to negate the momentum variable that we get at the end of integration so that the reverse transition probabilities are non-zero. And the acceptance probability is just the following. And another parameter that people want to optimize is the integration time. In the figure, that was shown is that E of t is the temporal averages along one trajectory, and then E of phi is the expected value, spatial value of the trajectory itself, and t is the integration time. So at the beginning, the error superlinearly decreases as it makes better and better estimations. But after a certain amount of integration time, it might not be computationally efficient to keep going because the relative decrease in the error is small. And this integration time depends on the target distribution itself. So this is the pseudocode for the Hamiltonian Monte Carlo Markov chain. So what we would have is the number of samples, target distribution, the joint probability distribution, integration time, and step size. And so I think for number 7, it should be just we take whatever Q naught would be, not sampling from the pi of Q, but instead we could either take it some constant. So, and we have to define the negative log normal log distributions of the what we have, as well as the gradient of the target distribution. And for the number of samples, we have the initial conditions, and we integrate it using the leapfrog integrator. And then we have the proposal, the Metropolis Hastings proposal. And then if we accept the proposal, then we take that as a sample that we have from the target distribution. So this GitHub has the Hamiltonian Monte Carlo Markov chain implementation that's readily scalable to multi-dimensional cases. And these are some of the results from that algorithm. So on the left is so for this one, I used for the target distribution was just a normal distribution with the variance of 0.1, and the kinetic energy, the joint probability distribution, I took it as a Gaussian with just a standard normal. And on the left is the samples that we have obtained for n equals to 2500. And on the right is 10 of the sample phase space trajectories in the position and momentum space. So we can see which, and since this is just a one-dimensional Gaussian, we can kind of reason that the concentric rings around the node should be those level sets of the typical set, which makes sense. So if you like to play around with other distributions or anything like that, here's the GitHub page. So finally, there's some extensions that people have worked on. So the 3 main parameters in the algorithm are the choice of integrators. So sometimes people use with the leapfrog, since it's first order, maybe the higher order cases have better accuracy and also better efficiency for some classes of target distributions. Also the choice of kinetic energies. So before I said that people normally use the Gaussian kinetic energy with the covariance that may be constant, but people have worked out cases where the covariance may depend on the position itself. And then finally the L and epsilon, the integration time and the step size. And there has been some work on a dynamic termination criterion that determine these 2 parameters dynamically as the trajectories are obtained. And it's called the no U-turn termination criterion. So those are some of the extensions that people have worked on. And that's all I have for today.
Did you feed the plot in the previous video? From the website?
No, I reran everything just on my computer with everything that I had. I think this was like a really nice example that they figured out all the different parameters.
So is this for a 1D case?
Yeah.
So can you explain like how you got the kinetic energy in this process? How you decided?
For this one, I just took the standard normal as the kinetic energy, and that was actually the one that they used in the example. I'm not sure, how they came up with this was
you start with one sample point anyway to get those rings? Or
Yeah, I think each of them corresponds to a specific. It should correspond to a specific initial point.
so you feed those initial points in, and then you get the whole curve.
Yeah. Which maybe it's also because of like all the parameters that they optimize for this specific example. Because like, I guess I would assume there would be some sort of a convergence to these rings before.
Do the colors mean anything in the second part?
Oh no.
So I'm wondering if like this algorithm gives you more samples near zero or less samples near away from zero.
I think it should be relatively unbiased, just because I think they're sampling from these like typical set regions, which ideally, I don't know if having enough number of samples could cover all the regions, but I don't think there is a bias towards any specific regions.
I think there's a question in the chat.
The momentum. So the momentum is just an a variable that people introduce to make it analogous to the physical case. And since what we have is just the target distribution in its parameter space, so we have one variable, but we introduce this auxiliary momentum variable P, so that, but we also have to make sure that the joint probability distribution on the resulting phase space is set so that when the auxiliary momentum is marginalized, we recover the target distribution in Q space. And once we introduce this momentum variable, then we can set the joint probability distribution as follows. And then that is related to the Hamiltonian with the second equation. And then once we have this form, then we can define these kinetic and potential energies in terms of what we know, the target distribution, and what we set as the conditional probability distribution.
How do you pick the momentum variable? Like what equations are used to pick momentum?
I think the momentum comes from the kinetic energy, this conditional probability, and most, I think they say practically using Gaussian is pretty useful, except we have to take care about the shape of the Gaussian.
Okay, we can thank Sungsoo for giving this talk.